it. Okay, so let me see. Okay, so we started off last class. We looked at the telescopic. So after that, we looked at the two-stage op-amp, right? So we looked at the case where we started off with the case where you don't want any zero at all. So in other words, you push the zero to infinity, correct? So we wrote down the poles and zeros. We added one big difference from the previous case. We added a resistor in series with the capacitor. So now what that does is it moves your zero to a new location, and it also adds a third pole. Okay, those are the two big differences by adding that resistor. Okay, you add a third pole, which on first glance it looks to be quite far away. Okay, so and the zero itself we can manipulate it using RF, so that we know. And the first case we looked at was this, setting RF to be 1 over GM2, which means you are basically pushing the zero to infinity. What happens if RF is not exactly 1 over GM2? What happens? Let us say RF is, RF minus 1 over GM2 is some small number. What happens? Yeah, still not a problem, right? Ideally you want to push it to infinity, but as long as it's very, very far away, it's not a big deal, because you are worried about it affecting your gain and your phase margin. In reality, as long as it's quite far away from omega u, you are happy. Okay, so your RF doesn't have to be exactly 1 over GM2. Right? So this is the case. Now suppose I tell you, you want, let us say in the first two cases, let us say I want 45-degree phase margin. What is the condition for 45-degree phase margin? Let us say in this case, yeah, let's take the case with these poles, right? What is the condition for 45-degree phase margin? Okay, so you can do that. So what is that? What do you think? What do you understand from the pole positions? How many poles do you have here? Actually, so in this case you have 3 poles. Let us start off with the case where, so you have 3 poles and you have pushed your zero to infinity. Correct? Your third pole is quite far out. That also you know. Okay? So what other condition can you derive? Second pole has to be at the unity gain frequency. Correct? Because the first pole is quite far in, it's the dominant pole. That is going to give 90 degrees. If the second pole is right at omega u, you will get 45 degrees from that. So you will have 45 degrees phase margin. Is that right? So now you can create a condition for that. Omega u is nothing but A0 times P1. Correct? So if you apply this condition, we know the positions of P2 and P1. So you already know it, and you know all of them, right? You know P2 is this. In other words, let's take the simplified version here. You know P1 is this. What is A0? It is GM1, GM2 over GO1, GO2. You also know that. Okay? So just apply this condition and you'll get CF equals GM1 over GM2 times C2. Okay? This is the condition you'll get. So all the GO1s get cancelled. It just happens to be a ratio of GM1 over GM2 times C2. C2 is quite possibly your load capacitance, right? Maybe then from the next time onwards, I'll just start calling it CL. Okay? So now, this happens to be the same value even if you do it for the previous case. Okay? Pretty straightforward. Now suppose, let's start off with the case. We also talked right at the end of class yesterday, we talked about setting RF not only equal to 1 over GM2, but even larger. Right? If we set RF much larger than 1 over GM2, what happens? So it goes all the way to infinity, comes back, wraps around and starts moving back. Correct? So at some point of time what you can do is, the other thing which some people proposed was cancelling. Which pole would you choose to cancel? Obviously P2. Right? The next non-dominant pole is the one you need to cancel. That will give you maximum phase margin. You have P1 dominant, P2 somewhere close. Let's say 45 degree phase margin is going to be at omega u, and then P3 is maybe far away. Cancelling P3 is no use. You are going to cancel P2. Okay? So you have P1, you have P2, and maybe you have P3, and you are going to put your 0 here, right on top. Okay? So that once you cancel it, your effective transfer function is only going to have two effective poles. One is P1, the same as before, dominant pole which sets the omega u. The other one is going to be P3, which is actually much far out. Right? So your phase margin is going to be much better. Okay? So this is what you want, right? Z1 equals P2 is the condition you want, right? They have to be exactly the same. Okay? So this is the condition you get. This is also pretty, pretty standard. So what this tells you is, so your resistor RF for exact cancellation has to be 1 over GM2 times CF plus C2 over CF. Okay? But now you have to be very careful, because if RF is not exactly the same as 1 over GM2, okay, what happens is your frequency response will probably look okay. Okay? Why? Because your phase margin may still be okay. Okay? Your 0 may start to increase, but then immediately your pole comes in and things come back to normal, or the other way around. Okay? However, if you look at the transient response, you will get a component, you will get an exponential component which, let's say you put a step response through this, right? Normally for a single pole you expect it to be a first order exponential, but if you add a pole 0 doublet, what you will see is there is a second exponential which actually depends, the time constant of which depends on the spacing between these two. Okay? In other words, as the spacing gets smaller and smaller, the time constant will get larger and larger. It will take longer and longer to settle. Okay, so that is why this is such a big problem. In the previous case, not a big problem. Here, it is a very big problem. Okay, so in today's class, what we are going to see is we are going to look at a couple of ways to generate this relationship. Right? You want this kind of inverse relationship. Okay, we'll look at a couple of ways. How do you make RF look like 1 over GM2? Okay, that is our basic plan for today. So before that, what we'll do is we'll see what happens if you need the phase margin of 45 degrees. In this case, P3 has to be at omega u, right? So this is the condition you get. Let's say in this case greater than or equal to. Because now you have cancelled out P2. P3 is the next pole. And to have 45 degree phase margin, P3 you can increase your omega u now. Right? Such that P3 is right at omega u. So now if you put in the expressions for P3 and so on. So we have the expressions for P3 here. Right? It's 1 over RF C1. Right, and we know RF in terms of CF and so on. So what we'll do is we'll put in all those expressions and you'll get something like this. Okay? Now in the previous case, so at the end of the day, what do you want to do? So let's go back to your previous case. What we actually want to find out is, so what are we doing here? We are actually designing a particular compensation capacitance CF. That is what we are designing here. right? The compensation network, CF and or RF. So if you are doing very simple compensation, you need to find out the value of CF for a particular phase margin, right? Because the value of CF you add, right, actually decides a number of things, because it decides how much your poles split, for example. Okay, so in a typical two-stage op-amp, apart from gain and other things, when you design your unity gain frequency and so on, you're actually designing this, because you're trying to design for a particular phase margin. Okay, that is why in the first case, so we looked at, from this condition, we looked at what CF should be. Now you want to solve for CF in the second case also. Obviously here it's a quadratic. Okay, it's not a simple linear equation like the previous cases, because RF also depends on CF for cancellation. You get something like this. Okay, all you have to do is just solve this quadratic for 45-degree phase margin. Okay. So what is this? I'm going to write it as GM1 over GM2 times C2, okay, times root of GM1. Rewrite it slightly differently. Okay. The reason we are going to write it like this, what is this? This is the case, this is the value of CF if you are trying to send your 0 to infinity. Correct? What is this? Ratio of the transconductances, root of that. It will typically be, I am going to say it's approximately 1, it may be slightly different, but they are going to be of the same order, quite possibly. What is this? By our assumptions, your load capacitance is dominating. Okay, so root of C1 was, we already assumed in all our cases C2 is much larger than C1. So typically this will be much less than 1. Okay, so you also get another insight. If you are trying to cancel the pole 0, your actual CF is probably going to be much smaller than the case when you, well, maybe not much smaller, but definitely smaller than the case when you are trying to send your 0 to infinity. Okay. Is that clear? Yes. Yes, of course, because pole 1 is the one you are trying to set the unity gain frequency. Sorry? Yes, that's right. Okay. Okay. So we look at a couple of ways of what is called tracking compensation. So now you want RF to track 1 over GM2 or the other way around. Okay, whichever way you want to call it. Okay. Okay. Before we do that, we need to understand a little bit more about what a two-stage op-amp looks like. Why now you are starting, suppose you want to generate a resistance which is proportional to 1 over GM2 or a GM2 which is proportional to 1 over resistance. We look at both cases. There are two ways you can do it, right? So to do that, now you are starting to look at circuit details. So now, so far we have been looking at block diagrams, GM1, GM2, just resistors and capacitors. Now we'll start to look at what exactly the two-stage op-amp looks like, at least the most common one. Okay? Let's start off with this. The GM1 stage. What is it going to look like? Diff pair with resistive loads Capacitive load, what, not capacitive loads, but active loads or what? What do you want here? You definitely want differential to single-ended, right? So the most commonly used pair we have seen is the diff pair with active load. Okay? So we'll start off with that. Okay, so I'll call this Vx, call this Vd, 0. Okay, so this is your GM1 stage. What is your GM2 stage going to look like? Okay, so you also have, this is your CF, this is your actual output voltage, and this is your GM2. Just a common source, right? Just a common source would give you a ground reference transconductance. That is what you want. That is the simplest case. Okay, would you use a common source NMOS or a common source PMOS? Why? Huh? Sorry? Okay, so what do you want this voltage to be biased at ideally? I would think that you would want it to be biased somewhere here close to this. It is probably, in fact, barring all mismatch, it is probably going to be biased there, right? So which one would you use? You have to use the PMOS, right? Look at where the DC voltage is. It is actually 1 VGS below VDD, right? So it makes sense to use the PMOS there. Okay. This is just a biasing, okay? So this is I1, this is I2. Okay? So I'll call this M7. M6 and M7. Okay? So now at last, we have an idea of what the two-stage op-amp is going to look like. Okay? This is what your two-stage op-amp is going to look like. We call this VB for now. Okay? Why do you have your capacitance? CF, and you have some, this is your C2. So it will be C2 will be CL plus whatever capacitances you have at parasitic capacitance you have at that node. Okay. Now you want to add a series resistance which is proportional to 1 over GM2. So what would you do? Let's look at the case where you want to add a resistance. Okay, sorry. You want to create a resistance which is 1 over GM2. How would you do that? Okay, so using a MOS transistor seems to make sense. You're trying to get something which is GM2. So let's start off by adding a real MOS transistor. So what I'm going to do is, I'm going to connect it to this node for now. I'll call this MA. This is CF. Okay. So first of all, why do you want to use a PMOS here? Why did I draw a PMOS, not an NMOS? Because in this case GM2, GM6, GM2 happens to be GM6. Okay, so I want you to try to use a PMOS here. Okay, so let us start off by connecting this. So let us say you connect it in this way. Okay, what happens? Do you think it will work? So let us say there is some process variation. This is I2. Okay, let us say I2 increases. What is going to happen to Vx? It decreases. What happens to RF, the effective RF, if Vx decreases? First of all, GM6 increases. So you ideally want RF to decrease, because remember it's inversely related. What happens in this case? If Vx decreases, right, your overdrive for your MOS in the triode region, in this case it is going to be in the triode region, there is no DC current through the MOSFET. Okay, overdrive is decreasing, so what happens to RF? It increases. So obviously this will not work. Okay, so what you really need to do is generate some voltage VA which is going to change in such a way that it is going to cause this to happen. Right? If Vx decreases in a certain manner, I2 increases. What happens to GM6? Increases. Right? What happens to Vx? You are basically having a same transistor, you are increasing the current. What happens to Vx? The gate source voltage also has to increase, right? In this case, source gate voltage has to increase. In which case, the overdrive VGS for MA decreases. If I had connected it to ground, if VA was ground. Okay, so definitely connecting it to ground is not the way. Okay, so what we'll do is, I'll erase part of this. The circuit which generates VA, I'm going to draw it on the left. Okay. Okay. So this is your basic current mirror with some IREF. Okay. Okay, and this I'll call this current I3. So now you can, oops, sorry, okay. Okay. What I'm going to do is, I'm going to generate VA depending on 2 diode drops from VDD. Why do I want to do that? What I'm going to do is, VA through this is actually a 2 diode drops through M6 and MA. Okay. I'm going to try to generate that using 2 diodes which are in the saturation region. If you do this, then you can relate, if you make sure that for example M9 and M6 have the same VSG, okay, then your the VSG of M10 will be equal to the VSG of MA. Everybody sees that? Okay. What is VA? VDD minus VSG6 minus VSGA. Correct? What is it? VDD minus VSG9 minus VSG10. So VSG10. Okay? If I make sure that these two have the same, the currents can be different, but I can make sure that I can size them such that the VSGs are the same. If I do that, then M10 and MA will have the same VSG. Okay? What is effective RF in this case? Sorry, you had a question? Yes. Okay. If there is some load DC current, yes, you are right. If there is some load DC current, that is true. Okay? We'll take care of that. We'll look at the other case and see if that actually helps with that. Okay? You are right though. If there is a load DC current, this could be a problem, because now you would mismatch the DC currents in the two cases. Okay? He has a valid point. But in this case, we are just looking at capacitive connections. Okay? And small signal. What is RF here? I have a MOSFET MA in the triode region. What is the resistance of the MOSFET? What is it? Correct? Sorry, UP. Okay. What is GM6? Okay. I want 1 over. So this is what I want. Correct? And I've already established that this should be equal to sorry. Okay, you are going to design this such that VSG6 is going to be equal to VSG9. Right? Is that clear? this is also true. Okay, so the VSG of A should be the same as VSG of 10. So now you can put these things in here into this equation. Substitute everything. Expression for RF, expression for GM6, and replace things by, replace, for example, VSG6 with VSG10 and so on. You'll get a condition on what? Relationship between MA and M10, for example, in this case, M9, M10. Okay? That is from here. Okay? I'm just inverting this relation. 1 over RF is GM6 into CF over CF plus CL. This is the relation. So you have VD sat 6, VD sat 10 over CF plus CL. Now VD sat, you can write it in terms of the current and the W over L of each transistor. Correct? And now you get a condition. So you already know M6, you know W over L6. Okay? W over L9 is easy to decide, so it just depends on the ratio of the currents. Right? You want the same VSG. So if you want VA to track, W over LA is related to W over L10. That is what it tells you. So this is your relationship. Okay? Everything is clear so far? You started off trying to generate an RF which is proportional to 1 over GM6 in this case, small GM6. To do that, we started off using a MOSFET in the triode region, a PMOS in this case because you have a PMOS in GM2. And the PMOS resistance in triode region, it's similar to the GM in the saturation region. Okay? You wanted to change VSG depending on the ratio of the currents and the sizes of those transistors. And now you've got a nice little relation to set that, to set W over L of A. So there is no unique, that is the idea, there is no unique set of values. Right? So you need to choose you can choose a certain, depending on, let's say, the current. Let's say you choose a certain I3. Right? You can choose a certain, maybe based on bias values. Right? Bias voltages. You can choose, based on I3, you can choose W over L10 for a given current density. Then based on that, you can choose your W over LA. In this case, you actually have two variables. So there may not be one unique solution. You understand? So to satisfy the relation where RF tracks GM6, If you choose, let's say, one value of W over L10, let's say 100, you will get a certain value of W over LA, the value of the MOSFET, which is in triode region. If you're going to make that 50, then this will change correspondingly. That is all. That's all this means. Well, not anything. There are certain numbers, right? So obviously, if you choose very small values for M10, you have to worry about headroom for this guy. Too much drop from VDD to ground. So it's not unlimited. Right? It's not completely unlimited. So there is a certain range of values over which you can choose current, you can choose M9, and you can choose M10. It is definitely not unlimited. Okay? I took RF as this is the relation you have based on pole zero cancellation. Z1 equals P2 gave you this relation. Right? That is what you want. Z1 equals P2 is what you are finally trying to achieve. That is what gave you this relation. And finally, that also gives you the value of RF, because RF does implicitly depend on CF. Sorry? If you had chosen M6 or MA as an NMOS, okay, you will get a mu n by mu p term, and mu n and mu p need not change. For example, with temperature they may or may not change the same way. Okay? How do you ensure that? MA is in triode. Well, because you have a capacitor in series, there is no bias current, right? So it is definitely going to act like a resistor. Huh? Yes. Well, yeah, but still you're still applying a small signal on top of your bias condition, right? What decides whether a transistor is in triode or not? The bias condition, right? After that you apply the small signal, and yeah, you could have a signal current flowing through it. There's no problem with that. But the signal current flowing through it will depend on the resistance, which depends on the bias condition. Right? Yes. Yes. Okay, so the resistance, yeah, yes, that's right. Okay, so first of all, ratios of W over L, let us say you are trying to do W over L1 to W over L2, those are actually very well controlled, right? I thought we studied this at the beginning when we studied ratios of resistors, ratios of capacitors. Those are all things which are very well controlled. Ratios of W over L, if you are trying to make one transistor for a certain quantity, make another transistor 2 times that or 3 times that, those are very well controlled, right? What you'll have to try and be careful is, maybe you might have to choose the currents and sizes carefully such that you may want to get rational numbers, for example, right? So that you can lay them out very easily. Definitely you don't want irrational numbers. You don't want to have, when you're trying to get, let's say if you're trying to mirror the current, right? You definitely don't want to have one size as 10, other size as 11.3417 or something like that, right? You definitely want to have laid out in units which can mirror your current very well. Okay? Your W over L, ratio of resistors, ratio of capacitors, and that's the other thing, right? CF over CL plus CF. That is also quite well controlled as long as they are the same type of capacitance. We looked at, there are actually MOSFET capacitances, there are passive capacitances, there are diode parasitic capacitances. So now we are assuming that CF is going to be a passive capacitance, and same thing with CL, and definitely CL dominates over the parasitic capacitances, and CL is of the same type, preferably. Right, so that CL over CL plus CF, which will track very well with process voltage and temperature. Right? Yes. Of course. Well, definitely, if you are designing an op-amp, you better know, right, what your expected load is. Correct? You may not want an expected load. It can also design for a maximum load. Obviously, if the as the load changes, your phase margin might change. Okay, that is fine. As long as in the worst condition you have good phase margin, you are happy. Just like the case where when we started off looking at it, the unity gain case was the worst case, right? You design for that, you definitely have good operation in other regions. That is the idea. Okay? Is that clear? Any questions? Yes. When you are doing step response, the region of MA might change. In what way? Okay. All of which current will get pushed into CF? We will discuss that when we come to slewing of two-stage op-amps. We have not covered that yet. Okay? Because so far we have looked at slewing of single stages. We have not looked at slewing of two-stage op-amps. When we come to that, we will discuss it. Okay? You are right. There will be a case where in two stages. So his question is, what happens when your input step is very large for the slew rate? So obviously, let's say this current is flowing like this. It not only has to charge CL, no, you have to charge CF also. Correct? Because you are trying to generate a very large voltage now, because V out is slewing. So obviously, correspondingly, there will be a current, slowing current flowing through the charging the capacitance. We'll discuss that once we finish up with the basic compensation and so on. We'll discuss that. Okay, what will happen? How will your slew rate of your two-stage op-amp change? Okay. Okay. So at that time that is true, but that's okay. Slewing is a very nonlinear phenomenon. Okay, and if it doesn't track, you can't do anything about it. What you are worried about is that this thing tracks very well for small signal cases when the op-amp is used in linear operation. So this is one case where we try to generate an RF based on 1 over GM2. What we'll do okay, Friday we want to have a tutorial, so maybe on Tuesday's class we'll try to look at it the other way, right? So let us say you want to use a resistor. How would you do it? Let us say you want to use a resistor RF. Then what do you need to do? You need to make sure your GM tracks the resistance. Okay? And you need to make sure your final, if you want pole zero cancellation, you need to get a relationship between a ratio of resistors. Right? In other words, RF should be proportional to some resistance. And if the resistance changes in one way with temperature, for example, it has a certain temperature coefficient, the other resistance is also going to vary the same way. Right? With process, it's going to vary the same way. So you have to use the same type of resistance. Okay? So we'll look at that in next class. Okay?